In the last video, I talked about how the method for solving these higher order differential equations is going to go as follows. First, we find the complementary solution. So this is the solution to the associated homogeneous equation. And we need to find n linearly independent solutions where n is equal to the order of the differential equation. Then we find any old particular solution, so one that works for the non-homogeneous version. Add these together to find the general form of the solution. So at this point, still the constants C1 through Cn have not been determined. And then in the last step, we use the initial conditions to figure out what those constants are. So I thought it would be a good idea to work through an example of this process so we can see how this works for this example right here of an initial value problem. So the first step is we're going to be looking for the solution to the differential, the complementary equation, which is this one right here. Now, we will look at a method for doing this in the next video clip, but for right now, you probably already noticed by just staring at it, if I said, hey, what are the solutions of this? Well, this is the same thing as saying, if I take the second derivative, I get minus 4 times the thing I started with. And from your experience with calculus, you could probably figure out without too much difficulty that cosine of 2x is a solution for that. And also that sine of 2x is a solution for that one. So, okay, so that tells us then that our general solution, our complementary solution is going to be C1 cosine 2x plus C2 sine 2x. All right. Then we need to find a particular solution. So for our particular solution, we say, okay, well, this forcing function here, 12x, it's simple enough that I can just sort of see, well, if I were to take 3x, then since it's a linear function, its second derivative would be 0. So this part would not contribute. And I would just have 4 times the thing itself. And 4 times 3x is 12x. So I'm going to take my yp to be 3x. And I say that's by inspection. And if you think that it's a lousy cop-out to say by inspection, yeah, sort of it is. But in the upcoming sections, so first we're going to look at how to find the complementary solutions. That'll be our the first thing that we do. The next thing that we do is come up with a better way than by inspection, and that'll be called the method of undetermined coefficients, so that we can solve these problems when they get to be a little bit more difficult. And in fact, we'll also look at another method for finding particular solutions called variation of parameters, which is even better. So that'll give us 2 strategies, both of these are ways for coming up with a particular solution. Okay, but for now, let's just take this one and pretend we're happy with it. So then the general form of the solution is going to be C1 cosine 2x plus C2 sine 2x plus 3x. And now that we have our general solution, we can go ahead and use our initial conditions to find C1 and C2. So if we evaluate at 0, we get 5. And if we evaluate our formula at 0, we get C1 times 1 plus C2 times 0 plus 0. And so then that tells us that C1 is equal to 5. And if we differentiate our function, or our general solution, we get y prime equals minus 2c1 sine 2x plus 2c2 cosine 2x plus 3. So if we evaluate that at the other condition, y prime of 0 equals 7. So that's the other initial condition that was given back at the beginning. Then evaluating this formula at 0, we have minus 2c1 times 0 plus 2c2 times 1 plus 3. And so let's see, so if we subtract the 3 from both sides, then we have 2c2 equals 4, so c2 has to be 2. Okay, and that tells us then that our solution is going to be 5 cosine 2x plus 2 sine 2x plus 3x. See where all this fuss comes in about why we need to have linearly independent solutions. Suppose that I had chosen y1 to be cosine 2x and y2 to be something that's dependent with respect to this set, or that would make a dependent set rather. So let's say 2 cosine 2x, so that the set of y1 and y2 is dependent. Now, with just two, dependent. With just two functions, the only way for this to be a dependent set is for one to be a scalar multiple of the other, so it looks a little bit dorky. But let's take a look at what would have happened. Well, then my general solution would have been c1 cosine 2x plus c2 2 cosine 2x plus 3x. And when I substitute in the initial conditions, I would have ended up with, so evaluating at x equals 0, this would have given me c1 plus 2c2 times cosine of 0 plus 0, and the initial condition was 5. And for the derivative, I would have gotten minus 2c1 plus 2c2 times sine of 0 plus 3 evaluated at 0 is 3 is equal to the initial condition 7. So this is my y of 0 initial condition, and this is my y prime initial condition. Now this one here is equal to 0, which means that this whole portion drops out right here, and I'm left with the equation 3 equals 7, and that's bad news. So no choice of C1 and C2 is going to get me out of that problem. So that's the sort of thing that you can run into if you don't have enough linearly independent solutions. And this is where the Wronskian comes in. So if we were to check the Wronskian of cosine 2x and sine 2x, is the determinant of cosine 2x sine 2x minus 2 sine 2x 2 cosine 2x. And when we evaluate this determinant, we have 2 times cosine squared plus 2 times sine squared. So the negative sign here cancels with the fact that this product comes with a negative sign, so that's why we get a positive term. And that just evaluates to 2, and 2 is not equal to 0, so that tells us that cosine 2x and sine 2x is independent, and hence a basis for our solution space.